All right, so we're going to look at look at this problem. So this is one from your book, E9.19. All right, so we find the power factor of the source and what is it, sort of a time domain expression for Vs. So we have the answer here. All right, one thing I'm going to point out right now, notice I've actually doctored the answer right here to say that this angle is positive. It is positive. Book actually indicates it is negative. It really is positive. Okay. All right, so just something to kind of bear in mind. All right, we'll get to that when we get to it. Now, if I want to find the power factor, all right, that's seen by the source, what I really have to do is I have to find S total, the total complex power, S total, the total complex power that is sourced by this guy. All right, if I think of this as what we call a transmission line, I can say that S total is S line plus S1 plus S2, where this is load 1, okay, load 1, and this is load 2, all right? This guy I'm going to refer to throughout as S loads, okay? All right, now I'm also told the voltage across the loads is 480 volts with 0 angle, all right? So my goal is to get this, right? Once I get this guy, I can get the power factor, and from that, I'll be able to figure out information about Vs, okay? All right, so to approach this problem, to start out with, I look at load 1 and load 2 separately to figure out what's happening with each of them. So for load 1, I can see that I've been told that it's 50 kilowatts at 0.82 power factor lagging. So P1 is 50,000, okay? So I know that the real power absorbed by that load is 50 kilowatts. I'm told the power factor 1 is 0.82, and it's a lagging power factor, all right? Whenever I have a lagging power factor, I know that I have an inductive type load. So I know the load looks like this. I know that Q1 is greater than 0. Has to be greater than 0 if it's lagging. This means it's absorbing Q. So absorbing Q1. Okay. So in this case, if I have a positive Q, the way I draw this is like so. Remember, I have S1 equals P1 plus JQ1. That has to be equal to VL times I1 conjugate. Okay. Focusing on this guy, I call this angle phi 1. Phi 1 is the angle of S1. All right. Given that S1 equals VL times I1 conjugate, that means that this must be angle of VL minus angle of I. All right, we'll talk more about that later. But I have phi 1. I drew this with a positive Q. Here's P1. And I call the length of this guy the magnitude S1. Okay. So in this case, what do I know? Well, I know the power factor, which is essentially the cosine of phi 1. Okay. And I know P. Now, looking at this just from a purely vector perspective, I know that opposite, which is Q, over adjacent, which is P, is the tangent of phi 1. So what I can say is that Q1 has to be P1 times tangent of phi 1. Okay? So I can say that, if I work through the math, 50,000, right, times the tangent of the power factor angle, right, like so. And then I can tell you what is S1, P1 plus J, Q1. All right, so to solve all of this problem, I wrote again a MATLAB script. All right, so I define everything here. And so I define things about both loads here. All right, but we can see real quick what I did. I said, okay, so phi 1 I said is A cos power factor 1. Okay, A cos is the inverse cosine or arc cosine. So I say P1 times the tangent of phi 1 is my Q1. And then I calculate my S1 there. Okay, so I get S1 is equal to my 50,000, so 5 times 10 to the 4th, plus J times 3.49 times 10 to the 4th. Okay, so that now is my complex power in load 1. Now I need to do load 2. So for load 2, what have I been given? For load 2, I've been given what I call the apparent power, which is the magnitude of the complex power. So that's 50 kVA. Okay. This guy, I'm told, is a power factor of 0.95 leading. All right, now when I have a leading power factor, what do I know? Well, I know my load is capacitive. So I know that my Q2, this guy, is a source of power. So he's sourcing Q2. All right, that means my Q is negative. All right, so that means that when I draw my vector relationship, here's the magnitude of S2, here's Q2, here's P2, here's phi 2. Okay, so Q2 is negative like that. All right, gotta remember that it's negative. All right, so in this case, if I want to get the angle, right, I say that phi 2, normally we would just say cosine inverse of the power factor. But in this case, I put a minus sign in there. Because remember, if I take the cosine of a positive number like this, I'm always going to get a positive angle. But I know the angle has to be negative because my Q2 is negative. All right, so I put that negative sign in there. All right, and I'll get an answer from that. And then in this case, it's pretty easy for me to figure out P and Q, right? I know that S2 equals P2 plus JQ2. All right, just knowing the vector relationships here, I can always say that this is magnitude of S2 times cosine of phi 2 plus J times magnitude of S2 times sine of phi 2, like that. Okay. All right, so go again to my MATLAB code. All right, and I've done that. Okay, so notice I have this new line here, magnitude of S2 times cosine phi 2 minus J magnitude S2 sine phi 2. Now, why did I put the minus sign here and I didn't put the minus sign here? Reason for that was because I didn't put a minus sign here, right? I could do it either way. Let me do it consistent with this, all right? I'll get the same answer. Okay, and there it is. S2 is equal to 4.75 times 10 to the 4th minus 1.5612 times 10 to the 4th J. So the negative Q2 came from that negative angle. If I look at phi 2 here, if I look at my phi 2, I see that it's negative. That's in radians, so I multiply by 180 over pi to get degrees. So negative 18 degrees, all right, for my phi 2. All right. All right. Now, what's next? Okay. What's next? Okay, so what's next for us is we need to figure out what S loads are. We need to find the total. All right. So S loads is equal to S1 plus S2. Okay. That's the total complex power absorbed by these guys. Now, what I could have done instead is I could figure out the current in load 1 and the current in load 2 and then do a KCL at this node to figure out the total current going through the transmission line. Okay? I don't want to do that. I could instead say what's the total current flowing into the combination of these loads by adding them up, right? And I could say that this has to equal to VL times I conjugate, where I is the current going into the combination of those two things, okay? Right? Basically what I'm doing is I'm combining the complex powers of these two things in parallel, lumping them as one load, saying the voltage across them is VL and the total current into them is I, right? I could look at it like this and say I equals I1 plus I2. If you plug that into there, you'll see I get the same exact result. Okay. Now, doing it this way, I see that my S loads, right, has to equal VL times I conjugate. Now, I want to break this up two ways, right? Now, sorry, I skipped a step on myself, right? S loads is equal to VL times I conjugate. So I get my magnitude relationship, which says the magnitude of S loads is equal to the magnitude of V times the magnitude of I. Remember, the magnitude of I is equal to the magnitude of I conjugate. The angle of I is equal to the negative angle I conjugate, and vice versa. So my angle relationship here is that the angle of S loads equals the angle of VL minus the angle of I. Okay? I always have those relationships that come out of this. So the angle of VL is 0, so I can see that the angle of I equals the negative angle of S loads, like that. All right, so what do I know? Well, let's go to my MATLAB script again. So here's S loads, is S1 plus S2. I take the magnitude of I by saying, give me the magnitude of S load. So in MATLAB, if I type the command abs, I get the magnitude of the vector, and I divide that by VL. So VL was just 480, right? And then phi I is the negative angle of S loads. And then I say that the phasor is the magnitude times e to the j angle. Okay, so I run that. Okay, and I end up with, let's see, abs I, so that I end up with I, the magnitude of it is 207.0614 amps, and the angle of I, 180 over pi, again, because MATLAB does radians, we got to convert to degrees, times angle of I. This guy works out to be negative 11.1899 degrees. Okay? All right. Now, knowing the angle, so basically knowing the phasor for I, right? Now I can figure out S line. One way to do that would be to say, well, here's the voltage V line, right? And I could say that S line equals V line times I conjugate. Right? V line times I conjugate. That's one way to do this, right? The other thing is, if I know the current through a set of impedances like this, I can say that P line is equal to I squared times the real part of the impedance. And I can say the Q line equals I squared times the imaginary part of the impedance. Okay. Now, if I try that, I squared times the real part of the impedance, right? The real part of the impedance always is R. The imaginary part of the impedance is always, in this case, omega L, or the reactive part of the impedance. All right, so this just works out to be I squared times, in this case, 0.2, and I squared, in this case, 0.4. Okay, so my code, I include that here, right? And then I add that to my S loads to get my S total. Okay, so I run that, copy it, paste it. Okay, and so now I get my S total. Okay, my S total, which is P line plus JQ line plus S loads, works out to be 1.0607 times 10 to the 5th plus J times 3.6437 times 10 to the 4th. Okay, all right, so I've got that. So now I need to find the power factor. Well, this guy is basically, can be expressed like so. So in terms of, the triangle, write it like this: P total, S total, here's Q total. So I can see right now that phi total there, I can see right now this guy has to be lagging power factor, right? Because I got a positive Q. All right, so go through the math right here, and I can say, what's the angle of this vector? All right, so the angle of S total, again, that's going to be in radians. I multiply by 180 over pi, so I see 18.958 degrees. If I take the cosine of that to get the power factor, 0.9458. Okay, so our power factor ends up being 0.9458. All right, now we compare that with what the book had predicted, 0.9457. Okay, now this is also a lagging power factor, and the reason it's lagging is because our Q was greater than 0. Okay, that tells me that the total load combination is somehow inductive. Okay, all right, so that better be the case that when I draw this, my voltage better have a situation where this is my Vs and this is my I. Better be the case that voltage is leading the current. All right, better be the case that voltage is leading the current. Let's see if that becomes the case. All right. Now, how do I get the voltage information? Well, I know S total equals Vs times I conjugate. So break this up again, right? Because I know magnitude of I is the same as the magnitude of I conjugate, and because I know that the negative angle of I is equal to the angle of I conjugate, okay, I can say that magnitude S total equals the magnitude of Vs times the magnitude of I, and I can say the angle of S total equals the angle of V minus the angle of I, meaning the angle of V, I guess I should say Vs, equals the angle of S total plus the angle of I. Right? At this point, I already know the magnitude and the angle of S total, and I know the magnitude and the angle of I. All right, so the magnitude of I, we already know. So the magnitude of Vs is the magnitude of S total divided by the magnitude of I total. All right, so if I do abs of S total divided by abs I get that this guy is 541.6688 volts. And I get that this angle, all right, so I do angle of S total plus angle of I, all right, I take that final result and I multiply it by 180 over pi to convert to degrees, and I get the angle of Vs is equal to 7.768 degrees. I'll round that to 7.77 degrees. Now, one thing about this, everything I have done up until now has been RMS. All right? Everything I've done has been RMS. And so if I want to get the actual time domain expression for Vs, that's going to be the square root of 2 times this value that I got right here, times cosine. We were told this was 60 hertz source, so 2 pi 60t, 2 pi 60t, plus the angle of Vs. So this guy works out to be, if I take my magnitude and multiply by the square root of 2, 766, so I get 766 cosine, so 2 pi 60 is 377t. The angle of Vs is 7.77 degrees. So let's compare that to the original answer. 765.94, 7.77 degrees, and boom, I see that's exactly what I got. Okay? All right, so this is a pretty typical sort of example. There's a couple of ways you could have done this, but I mean, I think if you follow through this example, you can kind of see. Again, as I always do, I recommend having something like this MATLAB code here, where if you make a mistake, you can easily see where you made a mistake in entering the equations, so you can kind of work everything out. All right, but this particular problem is a pretty typical sort of power systems problem. Very often my loads are defined to me in terms of the powers and reactive powers that those loads demand, as opposed to being told an impedance. And I might be told an impedance of a transmission line like I am right here. All right, and this is also pretty common where you say, well, the load has 480 volts. Utility is required to provide a certain level of voltage at an individual customer. And then V sub S needs to go up or down to make sure the customer gets that 480 depending on what this transmission line is. So it's not surprising if I look at this that the RMS value of the source is about 541. In other words, the RMS value of the source is a little bit higher than what the load voltage is, and it kind of has to be because of that loss through the transmission line. All right, so if you go through this problem, hopefully it's another good example of how to approach these sorts of problems.